Question number 51. If the solubility of AgCl in water is 10 raised to the power minus 5 molar, then the solubility of AgCl in 0.1 molar AgNO3 will be. In this case, first we have AgCl. Ag plus ion in aqueous solution you will obtain. Cl minus ion also is here. Now, in this case, solubility you know that is given 10 raised to the power minus 5 molar. So what would be the Ksp value in this case? Ksp value would be S square. So that can be written as 10 raised to the power minus 5 square. It is equal to 10 raised to the power minus 10 molar. This is Ksp for silver chloride. Now, this was the first case. Now you are just going to dissolve that AgCl in 0.1 molar AgNO3. It means in this case, we have AgCl once again in the solid state and it's getting changed into ions. And here you need to just find out the solubility in this case. We don't know what is the solubility, but we know the Ksp value, that is constant for AgCl. Now, if I talk about Cl, we can assume that solubility is S. But if I talk about Ag positive ion, we don't know about its solubility, but in this case, we can assume S is the solubility, and due to the presence of the common ion, those are coming from AgNO3, the concentration would be S plus 0.1, because we know that when AgNO3 dissociate, there would be the formation of silver ion and those concentration would be 0.1 molar. So in this, I'll just add 0.1. Now, what would be Ksp? Ksp is 10 raised to the power minus 10 that we have already calculated is equals to S plus 0.1 into S. We know that solubility of silver ion are very less in AgCl as compared to AgNO3. That's why S plus 0.1 can be considered as 0.1. Here is S and that is 10 raised to the power minus 10. In this way, the value of S is equals to 10 raised to the power minus 10 divided by 0.1. This can be written as 10 raised to the power minus 9 molar. And where this value is given? This value is correctly given here in option 4. So just choose option 4 as your correct answer. Question number 52. The number of moles of K2Cr2O7 required to oxidize 2 moles of ferrous oxalate in acidic medium is. We have K2Cr2O7 in acidic medium. It means what happened to this? In acidic medium, it gets reduced in chromium ions this way. And what about the other species? That is ferrous oxalate. Ferrous oxalate is FeC2O4. So, whenever it oxidizes, it forms Fe3+. Because it was in Fe2+ state, getting oxidized, Fe3+, CO2 is released. Along with that, 3 electrons are required in this case. While if I talk about the previous reaction in which K2Cr2O7 is there in acidic medium, in this case, the total number of electron required, 6. So, N factor we know in this particular case. Now, if you know the N factor, you can easily compare the milli equivalence of these two species. In this case, the milli equivalence of K2Cr2O7 should be equal to the milli equivalence of ferrous oxalate, that is FeC2O4. These two should be equal. What would be the milli equivalence of potassium dichromate? These are the moles of potassium dichromate multiplied by its N factor, that is 6. That should be equal to moles of ferrous oxalate multiplied by its N factor. Its N factor is 3. But what are the moles of ferrous oxalate? This is clearly given in the question. You have 2 moles of ferrous oxalate, and to oxidize them you need the total number of potassium dichromate moles. So here 2 moles are present. So the number of moles of K2Cr2O7 required, and if it is so, option 2 is your correct answer. Just choose that. After that, question number 53. Match the terms in column 1 with the terms of column 2 and assign the correct option. We have column 1 given here in which several processes are given. Zone refining, leaching, distillation, froth flotation process. Further, column 2 consists of different methods: concentration of lead sulfide, refining of impure zinc, ultra pure silicon, refining of impure copper, and concentration of bauxite. So these are the constituents of column 2. We have to match them. If I talk about the first process, that is zone refining, that is done for obtaining ultra pure silicon that is used in semiconductors, that is used as semiconductor. So in this case, you can match A with 3. Now, what about the second process? Leaching process. If I talk about leaching, this is used for the concentration of bauxite. Even this process is also used for the concentration of gold or silver also. So in this case, you can match this B with fifth one. After that, we have distillation process. This distillation process is used for the refining of impure zinc. And if I talk about Froth flotation process, this process is generally used for the purification of sulfide ore. And if I talk about lead sulfide, this is sulfide ore. That's why D can be matched with first one. Now, on the basis of this, A is matched with 3, B is matched with 5, C is matched with 2, and D is matched with 1. We can easily choose correct option, that is option 3. And now, this is your correct answer. After that, now question number 54. Select the pair of ions in which both species do not contain SS linkage. It means we have to first check the ions given here. First is S2O7 2 negative. Then here is S2O8 2 negative in first option. In the second option there is S2O6 2 negative. Then S2O3 2 negative. Then S4O6 2 negative. Once again, S2O8 is given, that we have already written here. Further, S2O6 is written, S2O6 2 negative, that we have already written here, and S2O7 2 negative. It means 5 different ionic species are given, and we need to just find out that pair of ions in which both species do not contain SS linkage. For that, I have the structures of all these species given here. Just have a look on that. S2O7 2 negative. In this species, there is no direct sulfur-sulfur linkage. It means this is not containing SS linkage. Further, in S2O8 2 negative also there is no sulfur-sulfur linkage. Further, in third complex, in third ion S2O6 2 negative, there is sulfur-sulfur linkage which is present. In S2O3 2 negative, there is also sulfur-sulfur linkage. Further, in S4O6 2 negative also there is sulfur-sulfur linkage. It means these two species are present in option 1. That's why I'll choose option 1 as my correct answer. I hope this question is clear to you. Let's take next question. Question number 55. John-Taylor effect is predominantly observed in low spin complexes having configuration. If I talk about John-Taylor effect, that is predominantly observed in the complexes in which unsymmetrically filled orbitals are present. And if I talk about D7 configuration, suppose I'm talking about D7 configuration where seven electrons are there in this way, and if I talk about the filling of electron in orbital, 2 energy levels are there. This is EG level and this is T2G level. In T2G level, lower energy is there, paired electrons are present, low spin complex we are talking about, so 7 electrons are filled in this way. If we talk about EG set of the orbital, that is unsymmetrically filled, and that's why in this case we will observe John-Taylor effect, and option 2 becomes correct option in this case. After that, question number 56 I have.